Hello everybody and welcome to today's e-seminar on the Enhanced Abaqus Welding Interface. The first of today's presenter is Murali. Murali is a technical sales director and a technical expert. He has a master's degree in engineering mechanics from the Indian Institute of Technology and a PhD in computational mechanics. He has over 20 years experience in theoretical and applied FEA and has co-authored publications and presentations in the field. His area of technical expertise include advanced material models, composites, fracture and failure, and Abaqus user subroutines. The second of today's presenter is Mike. Mike is a Smulia expert solution consultant. He has a master's degree from the University of Colorado and has worked for Dassault Systems for 25 years. He started in support and worked briefly in the Explicit Dynamics group before moving to Abaqus CAE Development Group. For the past 12 years, he has worked in the South Office in Texas, working on scripting and customization of Abaqus CAE. So I'm now going to hand over to Murali to begin.
Thank you, Jessica. Good afternoon, everyone. My name is Murali Pandiradi, as Jessica mentioned. I'm speaking to you today from the Smulia Great Lakes office in Cleveland, Ohio, in the United States. Thanks again for your valuable time in attending this presentation on the enhancements in the Abaqus Welding Interface. I will start with a brief PowerPoint presentation and then hand over to my colleague Mike Schubert from the Smulia South Office in Dallas, Texas, for walking you through a video demo of the new AWI. So for those of you who may not know, Mike is actually the developer of the AWI plugin. The slide on the screen shows the agenda for today. So after a quick background review of AWI, we will spend some time talking about the highlights of the new underlying analysis methodology that drove the rewrite of the current AWI plugin. Then we'll review a couple of examples that were set up and solved using the new capability. Mike will then take over for the demo portion. We will conclude with the Q&A. We value any feedback, questions, or comments you might have. For centuries, welding has been an integral part of the manufacturing process, as you all know. There are multiple welding methods, such as gas metal arc welding, shielded metal arc welding, laser beam welding, friction welding, and so on and so forth. During welding, the parts to be joined or welded together are melted near the joint, and the filler material is added to form a weld pool that cools to form a joint. Welding is a sophisticated process, which is an indispensable part of many industries, including automotive, aerospace, electric power utilities, shipbuilding, etc. During welding, the material undergoes drastic temperature cycles, resulting in residual stresses that then lead to distortion of the welded part. So modeling the welding process can provide important insight into the behavior of the joint structure after the welding. The first generation of Abaqus Welding Interface was released around 2010-2011 and was a very successful free add-on or plugin, as we call it, for Abaqus CAE. On the screen, you're seeing a snapshot from that GUI of the current AWI. It modeled the process as a sequentially coupled thermal stress analysis, since the physics is unidirectionally coupled between the temperature and the stress models. It was based on the traditional model change technology that we use to activate material during the analysis. And the material was added to the system at prescribed temperature, in this case, the melt temperature. Welding process is quite similar to a few additive manufacturing or AM processes, as you may already know. So for example, the welding process has similarity to an extrusion-based AM process like the FDM or the fusion deposition modeling, since we are adding large chunks of molten material. It's also similar to certain powder bed processes where there's a heat source, typically laser, that melts the material. So you might be wondering why we are talking about AM in this particular seminar on welding. So in fact, a few of our customers started modeling at the manufacturing processes using the Abaqus Welding Interface and capabilities, the solar capabilities in Abaqus. But soon they stumbled upon bottlenecks and deficiencies and approached us for help. And that then triggered multiple development activities. So last year, our R&D put in a number of resources and capabilities in the code to develop technologies for modeling AM processes. So methods were developed for AM processes like FDM, powder bed laser method, and so on. So for the modeling of welding process, we just took parts of both the workflow and were able to create the welding workflow. Once the workflow was developed, the AWI was rewritten from scratch as the second generation new and improved AWI, which we now refer to as AWI Pro. So on this slide, we have summarized the enhancements in the new AWI. So the feedback from customers who use the old AWI for modeling AM process is that model change was not scalable or practical. So a new functionality was developed to handle the additional material during the analysis without having to create a new step. So in other words, activate the material at the increment level rather than at the step level in an Abaqus analysis. So we use the term element progressive activation for this new technique. So in the new AWI, we don't use the model change, we use the new technique labeled as element progressive activation. Now coming to the heat input, in the first generation of AWI, we had the welding torch represented by activating the bead material chunks at the melt temperature. In other words, it wasn't a flux-based input, but prescribed temperature. So you bring in the material at the melt temperature. Now in the new AWI, we have implemented the double ellipsoid Goldach model for the heat input. So later on, we'll see a little more detail on this. The third major improvement is for the cooling of the welded parts, convective and radiative cooling. So we used to have the film and radiation conditions defined on the exterior boundary, and the plugin would create the needed definitions for each analysis step to account for the evolving boundary surface during the welding process. So that was in the old AWI. In the new version, it is now handled by the solver automatically. That is, applying filament radiation on the evolving boundary surface. The user simply has to specify that it is needed during the model setup inside AWI. Lastly, we have the GUI performance. The current version of AWI is completely rewritten from scratch using faster algorithm for the pre-processing of the model. So you'll get a first look of the AWI Pro later when Mike gives the demo or plays the video demo. From the tests we have done, we are seeing up to 10 times increase in the pre-processing time or performance for typical multi-pass 3D models. So this slide summarizes an example that shows that model change is not scalable. So we use a very small model with about 50,000 elements, and we are simulating the build. So we analyzed two different scenarios. In one case, the elements were added over 288 steps. You should interpret step to mean discrete chunks of material. And in the second scenario, it was a more refined or more accurate simulation following the material addition more closely, resulting in over 2,300 steps, or the number of discrete chunks of material that were added during the analysis. So as the chart on the right shows, you can see that there's a considerable speed up using the new method, and the speed increases with the number of steps. So you can see with when we have 2,304 steps, the new material activation, we have about 17 times speed up as compared to the model change method. So this is because memory requirements for model change increases linearly with more steps, whereas for the new method, we just use single step definition in Abaqus when simulating the process. Now let's look at some of the underlying analysis concepts of methodology. The animation on the slide that you see is from a heat transfer analysis of a structure with dozens of welds set up using the new AWI. So digging into the underlying analysis methodology a little further, we still use the standard sequentially coupled thermal stress analysis workflow. So there is a heat transfer analysis and followed by a stress analysis. So in both, there is material activation that takes place. But in the heat transfer analysis, of course, we have to model the torch energy input. So we have Goldak double ellipsoid model implemented as a special subroutine in this version of the plugin. And also in the heat transfer model, there is cooling from the exterior surfaces that we refer to, basically film and radiative cooling from the evolving surfaces as well as the original exterior surfaces of the part or assembly that is being welded. Stress analysis, of course, you prescribe the temperature loading, temperature history as loading, and that temperature comes from the heat transfer results. Let's talk a little bit more about material activation. So this is the end result is similar to model change, but it is handled differently and more efficiently in the code through subroutines. So elements get activated, for example, in the heat transfer as well as the stress model based on the torch location, the current location of the torch. The user can also specify an activation offset. So as you can see from this little animation, so if the torch center is here, based on the activation offset, that determines the extent of material that gets activated in the analysis. And the elements get activated at a given temperature, which is really the initial temperature that you define. So in the heat transfer models, that will be the ambient or the room temperature typically for the whole assembly, that is the base material and the weld material. Whereas in the stress model, the weld material will be initialized to close to melt temperature, whereas the base material would be at the ambient or the room temperature. The element or the material activation is implemented in this new user subroutine called UEP activation wall. And in fact, even though there is an algorithm currently implemented in there, it does give user more control in the sense that users can develop their own material activation algorithms if needed. As you will see later, a key requirement of material activation algorithm in the stress analysis is to ensure that there is no stress discontinuity when the material switches from inactive to active state. So in the past, using the model change, model change was the only option available to achieve this. So with this, with the new version, we have the more efficient progressive element activation capability. On the heating and cooling, as we talked about in the heat transfer, the elements are activated at constant temperature. Sorry, okay. So actually what we are listing here are the two separate techniques that are supported. So the first item, activating elements at constant temperature to represent the weld torch, that was what you had in the original AWI or the current version of the AWI. That is bringing the material at the melt temperature. So with the new version, we have the Goldak heating model supported, the double ellipsoidal model supported, using a new subroutine called UMD flex. So this can be used to create custom moving heating models as well. So if for some reason you want to use a model other than Goldak, you will be able to code that inside this UMD flex subroutine. So just showing the old styles. There are a lot of Abaqus users that may have implemented Goldak models using the D-flex subroutine. But in the new version, we have a separate subroutine UMD flex where the Goldak model has been implemented. And it's you can have one or more continuous moving fluxes, and it is also mesh independent in the sense that the torch motion is actually input as what we refer to as an event series, which gives the torch center coordinates and torch power as function of time. So the subroutine accesses this and other data from tables and other parameters, and activate the right elements and apply the right heat flux. The convective and radiative cooling we already talked about. So they are activated on active elements only, obviously, on the exterior surfaces as they evolve. And the keywords remain the same: star, film, star, radiate, except there are new load type labels to designate that they refer to applying those on evolving surfaces. Okay. On to the stress analysis. So again, as I mentioned, element activation or material activation is necessary in both heat transfer and stress analysis. And the stress analysis material activation follows what is done in the heat transfer procedure with some minor difference. For example, we don't use the activation offset in the stress analysis. So otherwise, it's very similar to how we do this in the heat transfer based on the torch path. And as I mentioned, the fundamental requirement for material activation in stress analysis is that it should maintain stress continuity as the material changes from inactive to active. And the temperature loading, it comes from the heat transfer results. And of course, you also typically would have temperature-dependent material properties, elastic and plastic properties. You may have phase transformation material models resulting in phase-dependent behavior. One other feature that we enforce in the stress model is a cutoff temperature. In other words, we cap the maximum temperature coming in from the heat transfer model at or close to the melt temperature, because we don't want the material to accumulate any thermal strains above that cutoff temperature. So we cap the temperatures at the cutoff temperature, which is about 80 or 85% of the melt temperature, melting point for the material. Okay, we'll quickly review a few examples where that were actually set up and solved using the new interface and the new solver capabilities. So the first one that you see on the screen here is a simple, quick energy balance verification. So basically, you take a simple, block of material, apply the heat flux using the Goldbach model. And let it on for a certain period of time, in this case 2 seconds, and you easily calculate what the total input energy is, and from the material property, specific heat and volume, you will be able to easily calculate what the delta T or the temperature rise in the material should be, and that's exactly what we recover after a steady state is reached. So the snapshot here is at about 20 seconds time. You do recover the temperature that you would expect based on the energy that you put in the material. So that's just a quick, simple verification. The next, we've done a couple of traditional benchmark problems. So what you see here on the screen is a 2-bead pipe benchmark, and there's a reference appearing here. In fact, this is the same problem that you would see in one of the published tech briefs based on the old AWI, where we had the prescribed temperature approach to model the torch. So it's the exact same problem, except here we have solved it using the new approach, and the charts basically show on the inside and outside surfaces of the pipe the temperature history and how it compares with the thermocouple data. The thermocouple data appears in the dotted lines here, and the solid lines correspond to the Abaqus predictions from the new approach for the temperature. So you can see there's a reasonable correlation between the predicted temperature profiles and the measured temperatures from the thermocouple. And here is another example, a simple flat plate model. This is actually just a 1-bead model, I believe, and you're seeing the temperature evolution as well as the stress evolution on the right. Again, this is a work in progress, testing this methodology on different problems. So we don't have all the results yet for all the different problems that we have tried, but this is an ongoing activity. So you can see here a couple of more pipe problems. So this is on the left-hand side. This is the same pipe problem where we compared the temperature history with the thermocouple data. And on the right, that is intersecting pipes. So this is a separate problem. So you can see the temperatures on the top and some plastic strain contours at the bottom. So let's play that for a few seconds there. All right, so I think that concludes the sort of the presentation, my part of that, just PowerPoint part of the seminar. And now I'll hand over to my colleague Mike to go over the video demo of the new AWI, or the AWI Pro as we call it. Mike?
All right, thank you, Murali. Welcome to a demo of the Abaqus Welding Interface. The AWI, as we call it, is a plugin that was developed for Abaqus CAE that specializes in setting up weld models. So when we bring it up, we see there's a tree here. We have options like bead color coding, highlighting, some QA tests. These are useful if you're new to the plugin. You can run some of the example problems and get the feel for how things are set up. There's a user's manual. This is an option for installing workshops, and then the post-processing. When we create a model in the welding interface, essentially we do a lot of work inside CAE before we do anything inside the AWI. So the first thing we would do is create a part that's going to have some welds in it. We would generate the geometry and the mesh and create the areas where the weld beads are. And then once that's done, I guess the next thing would be to create the material properties that are going to be used inside Abaqus CAE. And then once all that's done, then we can start, get to the point where we're ready to work on the Abaqus Welding Interface. So the first thing we do here is just we right-click and say Create, which it doesn't necessarily create a model, but it just initializes some things that we're going to need in the model. So when we're working the AWI, we typically are going to be working on the heat transfer model. And at the very end of the process, the AWI will automatically generate a stress model. So the sequence is, it uses a sequentially coupled analysis, does the heat transfer first, followed by the stress model. So in this case, we just have the one model. We're doing 3D. We're going to use the default unit systems of SI units, and we'll set some default initial temperatures, Stefan Boltzmann absolute 0. Okay, so we've just initialized a model, and then for that given model, we're going to have to go through these 5 steps. We're going to choose which materials we're going to use. We're going to select the parts and the welds and the weld beads. We're going to set some pass controls, and then inside here is where we create the Abaqus steps and define the passes that are being laid down. And then finally, the last step is just letting Abaqus, or the welding interface, generate everything it needs to do. This one, the manager. Okay, so the material manager, it displays which materials are available for the plugin to be able to use. And at this point, it shows no materials are actually available to be used by the AWI. It shows that there are materials that have been created, but we can't use them yet in the AWI. Now, the reason being is that the material properties that you would have created in Abaqus CAE, like the elastic, the plastic properties, thermal conductivity, and all of that, that defines just about everything we need. But we have to add one more thing essentially. So we're just going to click this button that says Make Available, and we're going to enter a stress cutoff. And what this is used for is in the stress model, if there are any peaks. Sharp peaks in the temperatures that are being read from the heat transfer model. Anything above 1600 degrees in this case would not add to the thermal strains. So we'll do the same thing here. All right. Now, so we've made these materials available. Now this third column is whether these materials include phase transformation. Now there is a plugin that allows us to use phase transformations in our materials. It's a separate UMAT. So the AWI is linked to that plugin, but we're not going to use it in this case. So you see now that we've modified a couple of materials, now we at least have something that we could use inside the weld model. So we see this green check indicating that we can move to the next step. So the next step, we're just going to choose which part is going to have welds in it, and we only have one part in this case. And we're then required to define the base region, the region that is not the weld. So we can either do it by picking on regions, or if we've got previously defined sets, which we do in this case. So if I go to highlight viewport, oops, well, I meant to zoom in here, and you can see that these welds are not included. We just included all of the base material cells. All right. And then another option is if you don't have any section assignments here, you can, and you know the section assignments are based on the base material and just the welds, then we can just choose to have the AWI fill that in for us. Okay. So you'll notice we still don't have a green check mark, meaning we haven't given it the AWI enough information to distinguish what region is what. So we've given it the base material, but now we have to let the AWI know which is the weld materials. So the first thing we're going to do is go through the first step is just assigning a mesh, which is really just assigning the element type. Now if you've already got element types you can assign, you can just hit OK, but in this case I don't, so I'm going to use just first order heat transfer, and then later on when the stress model is created, it'll use the corresponding stress elements. Okay, so the next step is actually define the welds. So we'll start with a small weld, give it a name, give it the material, and then you'll see the bead selection is popped up automatically. Now if you see the welds, this weld repository, now we have the small weld, we have beads, which is displaying as 0 beads have been selected. So that's what this dialog does. So now there are two ways of defining the beads, either geometry based or mesh based. So let's say that we are working on this. Now we have these three things that have to be selected: the bead itself, and then a torch path, which is essentially a selection of nodes along which the torch will travel, and then a starting point. Now typically the torch is going to be in the middle, kind of at the top of the bead and in the middle, let's say in this upper bead. So there's no edge there defined, so that we wouldn't be able to use geometry based, so we'll just use mesh based. So to make this a little bit easier, I'm going to remove a cell. Okay, so what I'm going to do is I'm going to pick on a cell face. That's the default. So I'm going to pick on that surface, and then to define the path, all I'm going to do is select on this one edge, and then the plugin will just march along this extruded shape to find the rest of the path. And then a start node. Alright, and since we're done with that weld, we'll hit cancel. I'm just hitting bead color coding. So if we put on bead highlighting, and I selected that, we could see the beads. All right. So that's our first weld. So the next one we're going to have to do is this one. So you notice we still don't have the check mark because we have base material that's been assigned, we got one of the beads, but this has not yet been assigned a weld. So we're going to create a new weld. Alright, we'll go through the same method. We'll remove the cell face. Alright. Now if we turn off the mesh here, oops, we can see these faces. Let's close this down. You can see these faces. These are just partitions that were created on this one face, just so we can define the 3 different beads in this case. So what I'm going to do is I'll go ahead and define this top bead first. So I'm going to do mesh base just like last time. Choosing a cell face, an element edge, and the starting point. Alright, and then I'm going to also use this option to remove the bead from the display. Okay, now if we look at our over here in the model tree, we'll see the bead's been created. Alright. So then I'm going to go ahead and go to the next bead. So we'll pick the cell face. We'll put an element edge here. Now you can understand why I use this option to remove the bead display, because I would not have been able to pick this element edge very easily. And finally the last one. Okay. Oops, I missed it. There we go. Okay, so you'll notice that the dialog disappears because all of the elements have either been assigned to the base or a weld. Alright, so if I can update. Oops. Okay, so we've got both beads, both welds assigned, got all the base material assigned. So now we're ready to define how the passes go down. Now, one thing I'm going to do here is I'm going to turn on highlighting. And if we look at it, bead 1, that's that center bead, and 2 and 3 and so on. Now in reality, that's not the order in which we're going to lay those things down. I defined them in that order just because it was convenient from a picking point of view. So what I'm going to do is I'm just going to reverse the regions. Now when I look at, here's weld bead 1, bead 2, and now bead 3 is in the center. All right. So now what we're going to do is go on through pass controls, turn off color coding, edit the pass controls. And what this does is it defines some default quantities for every bead that we lay down. Now we can override every one of these things, but it just makes it a lot easier to define a lot of this stuff. So for the first part, we have time incrementation, minimum time increment, initial time increment, so on, maximum number of increments, and allowable temperature change, and the default torch speed, cool down time, maybe we say 10 seconds between beads. We'll just use the default torch speed. And then here are the Goldac parameters. This defines our torch, and essentially we're defining all of these geometry constants of the shape of the torch. And now the other tabs here are for defining film and radiation loads. So let's say, the first line is the default, which is defining a film coefficient on the evolving beads. As the elements are being laid down, the exterior surface, which can have the heat radiated and convected, that surface is evolving over time. So this first line is just to define the film coefficients, and then if we're doing radiation, we can do the same thing. Now if we also want to, we can add other surfaces that have been defined. So let's say like this is the external surface, the internal surfaces. And we can just use the same numbers. All right. So that's our default film loads. It's our default step controls. Now let's go ahead and create the step in which we will lay down the beads. So we have two types of steps, a welding step or a user-defined step. User-defined step is just an empty step, so if you later on want to go add something to it, you can. But if we're defining how the welds are going to be laid down, so the first step, all it's doing is reading all those defaults that we just created. And here's the default film loads, radiation loads. We'll just keep everything just as it was. And then the next step is actually select which welds go down in that Abaqus step. So unlike the previous versions of the AWI, it would take many hundreds of steps to lay down weld beads. In this version, everything goes down in one Abaqus step. So I'm going to go ahead and choose to put both big weld and small weld down at the same time. And now you'll see that this check mark is done. So we've defined, let's just look at the big weld. So the big weld, we've got the 3 beads. We've got these color gray represents things that you cannot modify, you can't edit. So we have torch speed. If we want to change the torch speed, let's say we want to say 10 millimeters per second, that's really moving. Torch cooldown time. So the plug-in takes the path length, the torch speed, the cooldown time, and calculates the total time to put this weld down. Now there are 2 items up here, the weld start time if you want to have a delay. So if we're in this case, we're putting a big weld down, a small weld, we could put delays in when one of the welds starts. So by putting in 0, it just says it's going to start immediately at the beginning of that step. And then the initial weld temperature is what, and you'll notice it looks like that stress cutoff temperature. And what it is you're defining the initial temperature at which a weld is inserted. So when we activate an element, a weld element, it's presumed to be activated at or near melt temperature. So the default is this 1600, the stress cutoff temperature. All right, so the thing we're showing now is the torch movement controls. We can hide that and then display the Goldac parameters. Again, we can change any of these. And then finally we can display the parameters for defining the torch direction. So the difficulty with using the Goldac flux is that it is dependent on the orientation. So you do have to define an orientation. So we've put some automated methods in there for doing that. There's by centroid, by adjacent faces, and by a datum coordinate system. All right, so let's just take a look at what those do. So what I'm going to do is I'm going to draw just this one bead just to make it a little bit easier. Okay. And I'm going to click on this highlight in viewport. So what it's doing now is it's drawing the nodes, which is the path of the torch, and then the normal. So in this case, we're using bicentroid, and what that does is imagine, taking a cross section of this thing and taking this node and drawing a vector from this node to the centroid of that cross section, and that defines the torch normal. So, and usually that's a good approximation. So let's see. Now another option is by adjacent faces. Now what that does is, if we look at these nodes here, imagine just taking this face and this face, calculating the normals and averaging them, and that gives us our normal in the torch direction. So both of them are usually pretty accurate. In some cases, one might be better than the other. All right. So as long as we're satisfied with the orientations, then we could just accept it. Same with the small weld. We can go in and modify anything we want there. Then the final step, once all that's done, is we can just generate we call it the job step, but it's just generating all the things that are involved. So we give a heat transfer name, a stress model name, some output options. Let's say every 10 increments. And then the plugin does its thing. It goes off and creates all the keywords, the include files, creates the stress model, it does all the assignments. It does all the things behind the scenes. Okay, and that usually takes a minute or two. In some models, and maybe a little bit longer, but compared to the older versions, that step is probably 10 times faster than the older versions. So it goes fairly quickly. So anyways, that's a quick pass at the Abaqus Welding Interface. All right, now if we want to look at results, contouring results from the AWI, what we'll do is we'll go ahead and open up an existing ODB. This is results from one of the QA problems, essentially the same model. So the first thing I'm going to do is just change this animation. I guess that's okay. We'll put it about halfway in. We're going to slow down the animation a little bit, and then we're going to contour temperatures. And then this icon is what I'd mentioned earlier. It just forces CAE to just display only the active elements. All you have to do is just click on it, and then I'll just start an animation. So we see the temperatures, we see these two. This is just repeating the animation over and over again, but we see the two welds being laid down at the same time. So this is all done in a single Abaqus step. So now if we zoom in, we could see this one where these two beads were merged into the same pass. So it just forced into opposite directions, and then the final bead on top. So this will summarize the Abaqus Welding Interface demo. Thank you for attending. I appreciate it.
So just to summarize, so we talked about welding simulations and how the Abaqus Welding Interface had been such a successful plugin to model welding. And the first customers actually started using that for additive manufacturing simulations. So, and we saw how that triggered multiple solver and subroutine enhancements, both the R&D and the field, to efficiently model AM process. And now we have come a full circle using these enhancements for AM for our new generation AWI that we call AWI Pro. So then we covered from a very high level the new concepts for the new AWI. We talked about how we are moving away from the model change and have added moving heat source capabilities using the new subroutines. We have developed the subroutine for the gold back heating model or the double ellipsoid model, which will be provided with the tool. You also have the flexibility to create your own heating model, of course, using the subroutine framework. Then we saw some simple example problems set up and solved using the new approach, like the flat plate and the pipe welding problems. And finally, we got a sneak peek into the AWI GUI. Mike showed us a video demo on how to set up the model using the new AWI and showed all the new and exciting features that are part of the new AWI. So now I guess we'll open up for any questions or feedback you may have. Thank you.
All right.
I think we have some questions already, probably, right? Go ahead, Mike.
Yeah, I was going to say, the first question was, do we need a Fortran compiler to run the simulations? And the answer is yes, because all of these things are subroutine based.
Is this the offset parameter when setting up the heat source? So there was a question. Yeah. So the offset it's part of the gold back parameter input. So you give your A, B, CR, and CF, and there is an offset. So that offset basically sets the limit for the extent of the material to be activated ahead of the torch, and that's applicable both in the thermal model and the stress model. But as I mentioned briefly, in the stress model, we use a slightly smaller value of the offset.
The next one I saw is the stress cutoff not the exact same as using the star anneal keyword? And no, it's not. The stress cutoff, it's only used in thermal expansion to limit increments in thermal expansion. So it doesn't actually reset anything else. It just limits thermal expansion calculations.
Yeah. So basically, we say that it doesn't accumulate thermal strains above that cutoff temperature. So and we also cap the temperatures from the thermal model based on the magnitude of the stress cutoff. So hopefully that clarifies it.
So the next one, Ryan, maybe I think you could take this. This is what we've been investigating. Is what is the method used for activating elements?
Right. So the method used for material activation. The details obviously are proprietary, but it does what it is supposed to do, which is give you the behavior equivalent to model change. The basic feature of any material activation method should be that you can't have a jump in stress when the material goes from inactive to active, because what happens in general is that when the material is inactive, it is going along for the ride, but it does have a certain amount of elastic strains in it, and so certain magnitude of stress in it when it is active. But as soon as it becomes active, typically the stiffness, there is a big differential in the stiffness, and so you would see if you don't, if you're not careful, you will end up with a discontinuity in the stress. So our methods now address that discontinuity and make sure that the jump in the stress magnitude is avoided. So. And we do all that at an increment level without having to switch to a different step, which was the case for model change. Okay.
And then the next one was, is the method applicable to aluminum or any specific alloys? And really it's independent of material.
Right, yeah. Doesn't matter which material you're using. Would you please describe more about phase transformations? Glad you asked. We didn't. That's a topic we did not cover in this seminar, but we do have activities ongoing that incorporate phase transformations for a couple of different material classes. So there is one for steel, there is one for Ti-6-4. So these are currently developed as user material models, but again, how users get access to that, I mean, those are still big details still being worked out. But yeah, there is development going on that front. Which versions of Abaqus is AWI Pro compatible with? Does it require, excuse me, additional payment licenses? Mike?
Yeah, the AWI, it's only available in the new version of Abaqus 2017. Now, does it require additional payment and licenses? Well, we're still working out how we're going to distribute it. There are legal issues, we would like to lease it, but we haven't worked that out yet. But in the meantime, the old version is still freely available, and we're going to decide how to release the new version in probably the next 2 months. Okay, the next one was, can the Weld Torch weaving be defined?
Oh, sorry, I was going to take that and I was on mute, I didn't realize. Yeah, so there are a couple of papers you will see in the literature where torch weaving is addressed by, for example, in the transfers to the torch direction, you assume no variability in the flux. So those are tweaks to the Goldak model, for example. It can be done. That's why, you have this subroutine framework, UMD flux. The user is free to, code whatever moving heat source he or she is interested in. So the answer is yes, but it would require some modification to the existing subroutine, which is just a straightforward implementation of the Goldak model. But it can be done. So that is just, see, for example, sometimes you make approximations on the energy input. So you take the bead volume and then apply a constant volume flux to the entire bead. So it may give you different results compared to implementing the Goldak model directly, but again, if you're only interested in distortion or other aspects, so again, there are many different methods of simulating this, and that's why we give you the framework so that you can implement your own heat source model. Meshing is often time-consuming, time-intensive, and there are now rules since certain integrity assessment procedures for time controls and mesh sizes. Are there any plans for implementing any sort of automated meshing? Mike, you can elaborate on it, but I believe, I mean, that's sort of outside the scope of, what we presented here. I mean, meshing is a separate topic. Mike, do you have anything to add to that?
Well, I would just say, there's a list of things that we want to tackle next, and automatic remeshing is not there yet. We've still got to. So the next thing I'm going to do is the 2D version of this redone AWI. So that's what I'm doing this year. And then we've got a couple other things we're going to do with different ways of applying the energy of the torch. So that's probably also going to get done today or done this year. And then next year we'll probably start opening the RFEs up to what customers want. So we could start thinking about that then.
So there is a question, how can I also find out more about phase transformations and what formulations are included in the UMAT? Again, as I said, that is, we're still sorting out the logistics of how we make those available to the user, and once that happens, obviously there will be documentation associated with it, and you would have all the details of what specific phase transformation plasticity models and what specific approaches and what inputs, CCTs and things like that, what specific input is required for those models. So unfortunately at this time we are not able to provide you the details. Is it possible to get HAZ as a result? I mean, reduction of stiffness in MPa. HAZ, I mean, if it is just based on temperature contours, like setting a contour limit, I mean, you can always visualize those results. Mike, you want to add to that?
I was going to say the work being done on the phase transformation will let you look at the heat affected zone. So there'll be output variables that you can look at to see which materials have changed, and there's probably 20 different output variables that are in that work. But again, that's going to be a few more months before that's available also.
Yeah, with the phase transformation, of course, you get output variable that, a fraction of different phases at a given time snapshot, all that, many different variables you can contour plot.
Another question was, this proprietary technique, but presumably the input files and user subroutines show this. We are making the user subroutines available, so and how it all works with the AWI is transparent. So if you decide, oh, I want to do a different OLDAC flux or some other different way of activating things, all of those subroutines you're going to have available, so then you could go in and modify what we've done.
Yeah, I just want to clarify, the subroutines are available, and all you're telling Abaqus in the subroutine is whether the element should be activated at that time point or not. But how the activation actually happens, that is internal to the code. So, but users don't need to worry about that.
Yeah, that's a good point.
For active symmetric models, how does the AWI take into account 3D effects such as heat conduction ahead of and behind the torch? Actually, I don't know if you mentioned that. Currently, it's applicable only for 3D models, and I will let Mike explain further on the active symmetric in 2D.
Yeah, basically everything that we needed to do 2D is there except for one thing, and that's the evolving film surfaces as parts of the elements of the bead are being laid down. So that has not been done yet. So that's the only thing that really prevented us from doing the 2D work. But I've already talked with development, and they are going to add that during this development cycle. So I'll start doing the 2D work this year, and then as soon as the new release is out, then I can immediately turn the 2D on. So, but it's going to be another year before we have any 2D work ready for use.
Someone asked what validation has been carried out against real weld. That's again a work in progress. So we showed some sample results like thermal results comparison. So we continue to pursue that, and compare against existing benchmarks, but that's still something that we are currently focusing on. Really interested to know whether the runs only process through the CAE AWI interface, or does it generate an input deck that can then be processed on an HPC and modified manually? Of course, good question. Yeah, so that's one thing we want to emphasize. So the AWI or AWI Pro, that's an interface, and that helps you set up the models. Basically the pre-processing, which is the most cumbersome, most time-consuming aspect of setting up the weld models. Once you click that generate models option that Mike showed you, you have your input decks. As with any other Abaqus analysis, you can take it to the cluster, run it in parallel. In fact, that's how we run these examples on our end, on our clusters. So absolutely.
So thank you, Murali, and thank you, Mike. I'd just like to make everybody aware that today's e-seminar has been recorded, and everybody will receive the replay link to download it and play themselves in about 2 weeks' time. It will be on the Smoothie Learning community, where you can find lots of technical blogs from staff and customers. Thank you, everybody, for joining, and we hope to see you at another e-seminar very soon. Thank you again to Mike and Murali.
Thank you. Thanks, everyone.
Thanks, guys.